All right. Good afternoon, everyone. Thanks for joining today. Just checking one last thing on my end here. Okay, so I think we're good to go. 2 o'clock. See a couple more people rolling in, but I think we'll just get started here. So today I'll be presenting my webinar on dynamic mechanical analysis of silicone rubber and other rubbers for cold temperature applications. For those who are not familiar with C-Therm, I just want to give you a little kind of detail about us. Our purpose statement is simple, which is simplifying thermal conductivity testing for materials of tomorrow with their Trident unit. However, at C-Therm, we are also the proud distributors for Metravib DMAs in North America. Metravib DMAs are, I like to call them high-performance DMAs or dynamic mechanical analyzers. This is partly due to their unique capabilities, which includes a highly rigid one-piece test frame, which can provide accurate low-strain measurements because the machine won't deform. As well, it allows you to apply high forces to achieve high-strain testing. You can also test large specimens and are not limited to specific deformation modes. You have a large stiffness measurement test range as well, which allows you to test from soft specimens all the way to highly rigid specimens. And you can measure a material's viscoelastic properties from its glassy state all the way down to its rubbery state, which we'll see in one of the case studies today. It has high frequency testing capabilities, allowing you to measure directly the viscoelastic properties at high frequencies without the need of the WLF law or extrapolation. There's also some other unique features with the DMA that comes as well. One includes temporal signals. This allows you to analyze the measured signals to understand the damping behavior of materials in the linear and nonlinear range. This provides more accurate analysis for nonlinear materials. It allows you to do advanced energy calculations, and it just overall extends your capabilities of analysis, giving you more tools to understand your materials. There's also an automated solution called the Expander. It's a 6-axis robot arm designed to be a flexible automated solution. Currently, the Expander automates tests in tension, compression, and shear deformation modes. And this allows you to improve the throughput of DMA and fatigue testing, improves the accuracy of your test results by reducing human intervention. And it also has the flexibility to test finished products or other small samples. And that comes in hand with the 6-axis robot arm there. It's not just a DMA as well. There's fatigue testing options as well, which includes fatigue crack growth module, which turns your DMA Plus into a fatigue crack growth testing machine, as well as a DMA for a cost-effective solution. This was designed with a world leader in the tire industry. You can automatically monitor up to 4 cracks, and this follows the ISO 27727 standard. And since this uses a pure shear sample, you can do direct displacement control as well as force control as well. And just to kind of wrap up the product side of this presentation, I just want to finish off with a client testimonial. The DMA Plus 1000 from Metravib has been working very well and has increased our testing capability. We can now test rubber compounds under different geometrical modes as well as different deformation parameters. The service from the team at C-Therm has been excellent, and that was from Quillian McGlynn from Burla Carbon in the US. So now more to the technical side here. For those who are not familiar with DMA, dynamic mechanical analysis is a powerful tool to measure the viscoelastic properties of a material. DMA involves simultaneously applying an oscillatory deformation to a sample and measuring that response. Unlike elastic materials, however, viscoelastic materials will have a small phase angle or lag between the force and displacement response. This phase angle represents the viscous component of your viscoelastic material and is commonly called the loss angle, time lag, phase angle. There's a bunch of different names for it, but they all terms just associate with that slight discrepancy in time between your force and displacement signal or vice versa. And the way we can measure this viscous and elastic component is through the storage and loss modulus. The measured displacement and force used to calculate the complex stiffness, which is the amplitudes of our measured time signals, we can break that down with the following equation here, which is composed of our storage modulus, which is the amount of energy stored during a deformation, and our loss modulus, which is the amount of energy lost in the form of heat. And we can split these up by taking our phase angle to break up our complex modulus, where the sine delta or sine angle time lag can break down our complex modulus into our real component, the storage modulus, and the cosine delta can break down, can give us our loss modulus. And we can take the ratio of our loss modulus over our storage modulus to back solve to get our loss factor, which is just the tan delta, or the tan of that phase angle that we see in our measured signal. So it kind of comes back full circle. And these are all different ways that researchers will use to describe viscoelastic properties. So what can the DMA provide you? Well, it can provide you sample stiffness, material damping in the form of tan delta, material moduli, whether that's shear or elastic or flexural, compliance, viscosity. But the real value of DMA is it gives you the tools to control or to measure these material properties as the function of frequency, strain, temperature, and atmosphere. So it really helps you provide, it helps you get accurate measurements and replicate what conditions your material is seeing in real life. And you can calculate your modulus as a function. Oh, sorry, my camera's kind of drooping here. You can take your measured stiffness and you can relate that to modulus depending on what deformation mode you use. And I kind of mentioned this in a previous slide. With high force DMA, you're not limited to deforming your materials in one direction. You can, with a high force DMA, you can confidently measure your samples in tension to get your elastic modulus, compression to get your elastic modulus as well, dual lap shear, bending, which also gives you your flexural or elastic modulus. And there's other capabilities as well. The nice thing with a high force DMA is just you're not limited to sacrificing sample geometry to satisfy a low force constraint. So now I want to move on to a couple case studies here. So the first one is just going to be measuring the TG of silicone rubber. And this was something I presented at Rubber IEC earlier this year with the help of ARDL, who did all the testing for us. So I don't want to go into the full presentation, but I did want to take one experiment that I thought would be useful to set up why we or how we can measure the TG of a material and some important considerations to make while designing a temperature ramp test. Because this is something we commonly see, whether we're dealing with clients for in our thermal analysis lab where we do contract testing, or when we're helping fit a DMA for other customers as well for a larger purchase. So a temperature sweep involves heating or cooling a material from between two temperature points. And the goal of this temperature sweep is to understand the thermal transitions like glass transition temperature or the viscoelastic properties as a function of temperature. And you'll often pick these two temperature points as that are related to your operating temperatures plus a little bit more to get a full picture. And sometimes you'll push your material to the extremes to really understand what's happening here and to get a clear view of your material. The nice thing, again, with a high force DMA is that you can clearly measure the glassy region, which is often too stiff for some low force DMAs. So what do I mean by the glassy region, by the way? So the glassy region is the temperature region below the material's glass transition temperature. This is when the material will be hard and glass-like, as you can tell by the name, and it'll be very rigid. It'll act more like an elastic material compared to a viscoelastic material, but that changes once we heat up our material from the glassy region and move into the transition region and the rubbery plateau. And the reason I say transition region is because there's multiple ways to measure this glass transition temperature between the glassy region and the rubbery region. And it really depends on what method you're using, DSC, TMA, DMA, and even with DMA, you can measure this region by analyzing different viscoelastic properties as well, like your elastic modulus, your tan delta, and I'll kind of go through those in the case studies today as well. Okay. You have that question there, Landon, by the way. So then for the case study we did with ARDL there, we ran a test on silicone rubber on a Metravib DMA 2000 in tension following the ASTM standard D502615. And we wanted to measure the viscoelastic properties from -150 to 150 degrees Celsius. And we did this to understand the usable temperature range of a commercially available silicone rubber in cold applications. Silicone rubber has the benefit of having a large thermal stability range as well. It has a very low glass transition temperature, which contributes to that, which is measured to be around below -100, depending on the formulation used. And the properties we used for this test was a temperature rate of 1 degree Celsius per minute, the dynamic strain of 0.02%, as well as a frequency of 1 hertz. And one thing I did want to just clarify with this is just kind of highlight the reason why we picked these parameters here. So for temperature rate, we selected a smaller temperature rate to ensure consistent internal temperature. Typically, we're going to aim between 1 and 2 degrees Celsius, but it really depends on your own method for testing that. You can also add a soak time if you want to use a faster rate, like 5 degrees per minute or 10 degrees per minute. Most standards will specify on how much adequate soak time you need to perform that testing. And then the dynamic strain, we did it in the linear region. This is extremely important when doing a temperature sweep because you don't want to mix the effects of strain and temperature together. There's thermal expansion, your stiffness is changing, so there can be a lot of compounding effects when you're acting in the nonlinear region. So to just isolate your analysis to the temperature effect, it's always recommended to do your temperature sweep in the linear region. And if you're ever unsure if you're in the linear or nonlinear range of deformation, you can always do a quick strain or strain sweep at the start of your test. It takes a couple of minutes to do, and it can save you a vital amount of time compared to finding that out in a temperature sweep, which usually can take you anywhere between an hour to multiple hours, depending on the temperature range you're doing. And finally, frequency. So this one is really highly dependent, but it's always important to state your testing frequency as it will change your measured glass transition temperature. Similar to temperature rate, it's really just dependent on the ASTM standard used or the industry. Typically, an ASTM standard will recommend a lower frequency of like 1 to 5 hertz, which can be done on most DMAs. But however, there are certain industries where you want to test at higher frequencies as well. And just a tip there or something interesting to do is to do multiple frequencies during a temperature sweep. A temperature sweep, like I said, takes a very long time to do. So what you can do with a Metravib DMA, for example, is to run this temperature sweep while vibrating the material at different frequencies, and you can plot. It'll just give you more data while doing using the same amount of time for analysis to really see the effect of frequency on your TG, and it could give you vital information or understanding of your material at different frequency ranges. So here was the results that we got here. So we were able to detect the glass transition temperature below -100 degrees Celsius. And then we also unexpectedly noticed a large dip above -50, around -40 degrees Celsius, which we assumed at the time was due to crystallization or decrystallization of the material. And yeah, so by using the onset glass transition temperature, which is measured from the tangent of the slope and the plateau region of the elastic or the brittle glass region, We determined that the glass transition temperature was negative 129 degrees Celsius. And what was one of the highlights of our discussion at Rubber IEC was the amount of force needed to get this measurement. Typically, we think of a glass transition test as a very analytical test where you can run it on any DMA. But when you're in that brittle region, it takes a lot of force to deform that material, even with a very small amount of strain of 0.02%. So for this test, plotting the required force versus temperature, we saw that we needed a maximum of 49 newtons to clearly measure the glass the transition between the glass state to the rubbery state. And then one thing we did recently add to our discussion was just kind of analyzing that crystallization point at negative 40, where we hypothesized that would be due to crystallization due to literature search. We also tested this material on our Rigaku DSC Vesta, which we're also a proud distributor of. And we observed a small endothermic reaction, which helps support our argument that it looked like crystallization was happening at this temperature. So for our second case study, titled Improving Performance of Low Temperature Hydrogenated Acrylonitrile Butadiene Rubber Nanocomposites by using nanoclays, done by the Aerospace Research Institute of Material Processing and Technology in China. The work done by this group wanted to understand if they could improve the performance of rubber for sealing applications for cold temperatures. And they used a Metravib DMA 450, which is part of the older generation of Metravib DMAs, but still a very reliable unit. And they did a temperature sweep from negative 60 to 60 degrees Celsius to see the effects of temperature on the performance of the material. And they wanted to understand the change in low temperature performance of the rubber gaskets by, again, incorporating OMMT nanoclays into the material. They did these tests in compression to replicate the loading conditions that the materials would see in application. They did a temperature rate of 3 degrees C per minute. And frequency, which is a little bit different from what I talked about before, they did 125 hertz, which they didn't state in the paper, but I hypothesize that this is due to recreating those conditions that the material is seeing. If we backsolve that 125 hertz, we get about 7,500 RPMs. So I suspect they wanted to understand exactly what the material is acting like under compression with a very specific frequency. And here were the results that they got. So they found that increasing the concentration of their nanoclays decreased the glass transition temperature. This is important because this will, if you lower the glass transition temperature, your material will stay in the rubbery state at colder temperatures. Plotting the storage modulus versus temperature, they also saw that the increase in clays increased the elasticity of the material as well. And just for another quick case study here, titled Reactive Grafting of, I'm not a chemist, so I won't be able to say that full word clearly, but this group here was interested in evaluating the technique of grafting for silica in a rubber compound. And this is important because silica doesn't really like to play with rubber too often. You usually have to do some form of surface treatment to it. So this group here was analyzing a grafting procedure to see how it would change the tire performance of their rubber composite. And this was done in India at the Rubber Technology Center, Indian Institute of Technology. So they used a Metravib DMA 50 in tension. This is part of the desktop series that Metravib also offers. And they did a temperature sweep of negative 100 to 100 degrees Celsius. And the goal was to understand the tire performance of each compound. And for those who don't know, DMA has a lot of success in the tire industry due to the fact that it can evaluate key performance. It can evaluate the performance of tires with key performance indicators. Specifically, by measuring the tan delta at -10 can evaluate winter traction. You can use the tan delta at 0 degrees to evaluate wet traction. And then measuring the tan delta at 60 degrees Celsius, you can evaluate the rolling resistance of a rubber compound. There are other key performance indicators as well you can get from DMA to evaluate tire performance, but these were the three they were considering. They did, like I said, they did their test in tension with a temperature rate of 3 degrees C per minute, a dynamic strain of 0.1%, and a frequency of 10 hertz. So again, they did the driving frequency at a frequency that wasn't stated by an ASTM standard, but this is more driven by the industry, where 10 hertz is typically used in tires, or plus or minus a couple hertz, because this is the frequency that that replicates the speed of the tire rotation. So you'll typically see this in industry as well, where they just see or understand how the materials are predominantly loaded, or and then reverse engineer that to get a driving frequency. So from their tests here, they ran 3 different materials. They did a whole bunch of analysis, but I'm just going to focus on this one here, where they analyzed the rubber compounds with 3 different processes: the silica composite without any treatment, with silane added separately, and then their grafting process that they were evaluating. And what they found was that their process provided better tire properties. So higher winter traction by increasing the tan delta at -10, higher wet traction by increasing the tan delta at 0 degrees, and lowering the rolling resistance by lowering the tan delta at 60 degrees. And they attributed this due to the grafting process increasing silica dispersion for their materials. And that really finishes the presentation today on the case studies here. I do just want to have a couple closing notes. Metravib, if DMA is something that's really interesting for you, if you want to learn more, Metravib just released a new DMA white paper, which is available on their website there. I highly recommend if you're new to DMA, or if you just want to learn a little bit more or brush up on your skills. Just a very quick read, couple pages long, but highly educational and very informative. If there's other resources that you'd be interested in, you can always check out our website. We have old webinars. We have a tech library full of application notes, blog posts, and other journal articles. And if you're interested in even having a discussion with us, we'll be at a couple events in the near future. Well, one in the near future and one in the new year. So we'll be at the Thermal Management Expo in Europe this December, which is happening right now, actually. And then in the new year, we'll be down in California for the Plastic West show, which is part of the IME West conference down in Anaheim, California. And then we have one more webinar for the year. It's been a busy year of webinars, but Arya will be speaking on Thursday on our Flex TPS sensor and just giving a nice method overview. So if this is something, if thermal conductivity is new for you, if you want to learn a little bit more, this could be a great presentation to attend. Be sure to follow us on LinkedIn. We always release when we're doing upcoming webinars, new blog posts, or other exciting news is always just showcased on our LinkedIn page. Next steps, yeah, so if any of this was interesting for you, we'll be happy to book a demo for you to run some samples. You can always request a quote. I know it's end of year, but people are planning for their budgets next year. So if you need a quote or anything, feel free to reach out. And there's always, if you just have a technical question or if you want to have a discussion about DMA, I'd be happy to have that as well. You can contact me at travis.parkman@ctherm.com, but it'll be available in the email that we send out to you as well. So at this point in time, we'll be taking questions if anyone has any questions.